What we're going to talk about now is the history of parallelism support in Java. Earlier, we had talked about the history of concurrency support. Now we're going to do something similar for parallelism support. This will give you a perspective on the fork join pool model, the fork join framework, parallel streams, completable futures, and reactive streams. Those are the four main things that we're going to focus on in this class. We'll also talk briefly about the evolution of Java from concurrent programming support to parallel programming support. There was foundational parallelism support added in Java 7, which came out in 2010, and this was when the fork join pool capabilities were released. The focus there, as we've talked about, this is just kind of a recap, is on fine-grained, object-oriented data parallelism. So you've got objects, you subclass, you override, you fill in the parts that have to run in parallel, and then you let the framework do the computation. But you have to provide a lot of the scaffolding for that. And the way this works is it uses the split, apply, combine model, and that's kind of what you write in the compute method that you override from recursive task or recursive action and whatnot. And you fill in what happens when there's a small number or one element left. That's the basis case. And then otherwise, you split up into chunks. So that's the split, apply, combine model. You can read more about that parallel processing model here. Good example of this is something you can find in my GitHub repository. Uses the common fork join pool to search input strings to locate famous phrases by William Shakespeare, where each input string corresponds to a work of Shakespeare, like Hamlet or Macbeth. And then we have another file that has famous quotes, and it goes and looks for them and tries to find out where they occur. So that's a good example of a very embarrassingly parallel problem. The good part about this capability, the fork join pool, is it's very powerful, very scalable, but it's a bit tedious to program directly. You have to keep track of a bunch of stuff. And in particular, you have to keep track of things like whether or not you are going to have the base case of the recursion, how to split things up into pieces. You have to use inheritance. There's white box reuse. So it's not quite as easy as other stuff. Therefore, because there were some limitations with this approach, Java added support for parallel streams and completable futures in Java 8, which came out in 2014. These frameworks provide support for fine-grained functional programming. And one model, the streams model, and parallel streams in particular, supported data parallelism, where you take the data in some input, like a list or an array or whatnot, and you split it up into very small chunks, and then you process those chunks through a pipeline of so-called intermediate operations, which either transform or filter the data, and then you have what's called a terminal operation that triggers the whole thing and collects the results or does something with the results to get a final reduced result. The other model, which we will also talk about, of course, is the completable futures framework, which is about asynchronous processing, where you take one task and you kind of split it up into multiple tasks, and those tasks can run asynchronously. And as they complete, then they can either be further chained together in some kind of flow or pipeline, and they can also be combined or joined to get results that are composite results. So a very different model, programming-wise and analytically reasoning-wise than the parallel streams model, but they both give you support for functional programming and functional parallelism with different flavors or different themes. And then, of course, the other approach is, I should say, this is an example. This is an example of synchronously downloading images that aren't already cached from a list of URLs and then processing and storing the images in parallel. So this is the data parallelism part. This is parallel streams. You take some data, which is a list of URLs. You make this run in parallel. You get rid of things that aren't already cached. You get rid of things that are cached. You then download them, apply filters to transform them, and then collect the results into a list. Here's how you can combine streams and completable futures to asynchronously do those processing steps. So this involves doing all the steps asynchronously. And you can see we're still using a sequential stream to control the overall flow of data through this pipeline, but the actual computations at each step along the way are done in parallel and using completable futures and done asynchronously. So we'll look at both of these examples in a lot more detail later. Later, Java 9 and beyond had support for something called reactive streams, which is a publisher-subscriber style model. And this was provided in some ways we'll talk about here shortly via some interfaces called the Flow API. And then there are a whole bunch of different implementations like RxJava, Project Reactor, Akka, and so on that go ahead and refine those interfaces into actual frameworks for doing reactive, asynchronous, and parallel processing. And here's a simple example that uses the Project Reactor reactive streams model, which is somewhat similar in some ways to the parallel streams model, except it's just got some slightly different syntax and some slightly different semantics, and there's different thread pooling mechanisms, But this is the same kind of thing that we saw before. You'll actually find, at least for my money, that if you're just trying to do parallel computations, the parallel streams model is usually the most concise way of doing things. You see there's not a whole lot of stuff going on here. And the reactive streams model is very cool, but it's a little bit extra stuff. So we'll talk about those, and later you get a chance to see the pros and cons when we try to actually run these to see how they perform in practice. Spoiler alert, they perform about the same. These parallelism frameworks are designed to try to strike a balance between human productivity on one hand and performance on the other. Historically, if you wanted to make things run efficiently, you gave up some productivity by programming it at a low level using things like threads or CUDA or other low-level toolkits. Conversely, you could make things be more productive, but you would often give up performance by writing sequential code. So the nice thing is this gives you sort of the best of both worlds because you get stuff that scales up nicely, but it's fairly easy to program once you understand the programming model. However, the frameworks can be overly prescriptive. What does that mean? Well, they're great at abstracting away the low-level details, but they also limit fine-grained control over the parallelization process. Now, turns out there's all kinds of knobs that you can turn, and you can control lots of these steps. But if you had some really esoteric kind of programming model, then parallelism model, then this might be too constraining for you. And in particular, if the problem doesn't fit well into this sort of divide and conquer-like approach that splits things up into little chunks, applies things in parallel, and then combines the sub-results into a final reduced result, then it may not be the best way to go. Having said that, a lot of things work this way. There's also, of course, some overhead. There's no free lunch for task scheduling, data partitioning, and thread management. These frameworks are great because they abstract away from those aspects so you don't have to write them, but there is a little overhead. And so sometimes if you don't have the right scenario, for example, if you don't have a problem that has high N and high Q, then you can end up not having things run as quickly as if you wrote it at a lower level. In practice, that's usually not the big issue, but there could be some situations where you might have a problem. This is a meme that's based on a quote from the movie The Matrix that never happened. So everybody seems to think for some reason that I think is this Neo? I always forget who this guy is, but it's Lawrence Fishburne's character. He's supposedly saying, what if I told you that everything you knew was a lie? But apparently he actually never says that in the movie. So that will not be on the quiz, but that's a little bit of trivia. So let's talk quickly about the evolution of Java from concurrency to parallelism. There's a great talk by Brian Getz that talks about the evolution of Java from concurrent programming to parallel programming and parallel computing. You can see it here at this link. His talk explains how modern Java combines functional programming with fine-grained data parallelism from the fork join pool to leverage many core processors. Processors are going up and up and up in cores, but for a while, we really weren't getting a lot of speed up that we would have expected because we didn't have a good programming model. So data parallelism is one way to fix that particular glitch. There's also a nice talk by Rob Pike, which you can see at this link, where he talks about the difference between concurrency and parallelism. And he talks about how concurrency is involved with dealing with lots of things at once, whereas parallelism is about doing lots of things at once. So that's a nice way to compare and contrast those two paradigms. And then there's also a nice presentation and I guess there's a podcast and then a transcript of the podcast by a guy named Ron Pressler, who has been heavily involved with Java's structured concurrency model. I should point out, by the way, that Brian Getz has been heavily involved in Java parallel streams. Rob Pike has been heavily involved in Go and Go routines, which is the way that they do concurrency in Go, which is another programming language by Google. And then Ron Pressler has been involved in Java's concurrency approaches that are very modern. And he talks about how parallelism is about cooperating on a single thing and concurrency is about different things competing for resources. So those are three different ways of thinking about concurrency and parallelism. So that's the end of the discussion of the history of parallelism support in Java.